Distance measuring equipment, or as it is usually called, DME, is a secondary radar system that enables an aircraft to establish its range from a ground station. DME stations are often co-located with a VOR, which gives magnetic bearing from a suitable ground station. The two facilities together form the standard ICAO-approved Rho-Theta short-range line-of-sight navigation aid. Rho relates to range, and theta relates to bearing. The symbol for DME varies from chart to chart, and is shown on each chart legend. Here we see the legend on a topographical chart. Military aviators have a system similar to VOR DME called TACAN, which is short for Tactical Air Navigation Aid. The bearing element operates in the UHF band and is therefore not available to civilian aircraft. But the range element is identical to DME and can be used in exactly the same way. It has this symbol. Slightly different symbols are used in this Jeppesen en route chart. In this AIRAD high-level chart, the VOR frequency is underlined to indicate DME. Aircraft measure their distance from a ground station by emitting a series of double radio pulses or pulse pairs in all directions. These are called interrogation pulses. The ground station, the transponder, receives the aircraft's transmission, amplifies it, and then, after a 50 microseconds delay, retransmits it in all directions. These are called the response pulses. The airborne equipment measures the time interval between transmission, T1, and reception, T2, of each pulse pair. The 50 microsecond delay at the transponder is deducted from the total. Using this time interval and the known constant speed of propagation, it determines the slant range of the aircraft from the responder. If, for example, the transmission times of T1 and T2 total 30 microseconds, we convert microseconds to 10 to the minus 6, which gives us 4,500 meters. Divide by 1852 to convert the meters to nautical miles. We can calculate that the aircraft is 2.43 nautical miles from the transponder. A simplified way of calculating the range is based upon the fact that a radio wave takes 12.36 microseconds to travel a nautical mile in two directions, and this is known as a radar mile. So divide the time taken for the pulses to go and come back by 12.36, which gives the one-way distance. Pilots are not required to make these calculations in the air. The DME receiver and display unit carries out the conversion for us and displays the range in nautical miles. The range is measured directly between the aircraft and the ground station, and so the height of the aircraft above the beacon is a consideration. This range is known as slant range. However, what the pilot sees on his map, and what he usually requires, is the range to the point on the ground underneath the aircraft. This is called the plan range. The problem is easily solved by the use of Pythagoras' theorem. Let's consider an example. Say the height of the aircraft is 18,240 feet above the ground. If we divide the height by 6,080 feet, this gives us 3 nautical miles. Say the slant range is 5 nautical miles. This is a simple 3-4-5 triangle, and so the plan range is 4 nautical miles in this case. However, For the more general case, we use Pythagoras. The slant range equals the square root of the sum of the plan range squared and the height squared. Of course, they must all be in the same units. You cannot have ranges in nautical miles and height in feet. In fact, the more usual problem is finding the plan range from the slant range. With a little rearrangement, the equation becomes plan range equals the square root of slant range squared minus height squared. As a general rule, the difference between slant range and plan range does not cause a problem when the slant range is more than 3 times the height. But when the aircraft is close to the station, the range will become increasingly inaccurate. The ultimate case is the overhead. The aircraft is at 0 horizontal distance, but the DME will give the height as the range. DME range is useful information. A pilot can calculate his ground speed and elapsed times to the ground station. Some airborne equipment will do this automatically. He can comply with published procedures, such as ILS, procedure turns, and DME arcs. He can obtain a position line by using DME as a circle with the equipment in the center, or use a VOR radial with the DME to get an exact position. It facilitates radar identification when the pilot reports his VOR DME position, and he can comply with area navigation requirements. DME has an emission code of P0N. Its operating frequencies are between 962 and 1213 MHz in the UHF band at 1 MHz spacing. This provides 252 channels. A DME channel consists of 2 carrier wave frequencies, always 63 MHz apart. For example, if a carrier wave of 1025 MHz is used for the interrogation pulse train, the carrier wave frequency of 962 MHz is used for the response pulse train. The response pulse train is always delayed by 50 microseconds, which allows enough time after the receipt of the interrogation pulses for any multipath echoes to arrive and be ignored before the response pulse is sent. The delay is called the echo protection circuit. The carrier wave frequency is changed at the ground station for 2 reasons. Firstly, the aircraft will receive reflections of its interrogation pulse pair either from the ground below or from heavy clouds. In order to distinguish these reflections from the response pulses, the transponder emission is always 63 MHz, either below or above the interrogation pulses. Secondly, if no change of frequency were made at the transponder itself could become self-triggering. This would occur whenever a response pulse from the ground station bounced off a nearby surface or cloud and returned to the transponder, simulating a further interrogation pulse. Let's look in more detail at this pulse technique. Each aircraft's interrogator is programmed to transmit its paired pulses at random intervals. That is, the transmission sequence of pulses, also called the pulse repetition frequency, PRF, is irregular or jittered. This differentiates its pulses from those of other aircraft. The use of twin pulses ensures that the receivers never accept matching randomized single pulses which could possibly emanate from other radars, ignition systems, or lighting. When a ground station, the transponder, receives an interrogation pulse, it sets up gates to match the random PRF pulse repetition frequency of the transmitted twin pulses. Electronic gates essentially blank out signals with other patterns. The responses on the transponder's carrier frequency include an individual aircraft's paired pulses plus those from other aircraft. The receiving equipment of an aircraft is designed so that only the responses which match its PRF are allowed through the gates. The pulses have now achieved lock-on, and the DME leaves search mode and enters tracking mode. Just in case the interrogation or response is interrupted, airborne equipment has a memory of about 10 seconds, which continues the display until the signal returns. During this period, the equipment is prevented from starting a new search. As the aircraft's range varies, the gates move to accommodate the corresponding increase or decrease in time between transmission and reception of the twin pulses. This lock and follow technique ensures that the returning twin pulses are continuously tracked. To achieve rapid lock-on during the range search, the interrogator transmits at 150 pulse pairs per second for 100 seconds, or until lock-on is achieved. If lock-on is not achieved, it will then reduce the search rate to 60 pulse pairs per second, and continue at this rate until there is a range lock-on or the channel is changed. At lock-on, the rate will reduce to 25 pulse pairs per second. Lock-on in modern aircraft takes about a second. Older analog equipment will take much longer. It is assumed that 95% of aircraft using a ground beacon will be in the tracking mode and not exceeding 25 pulse pairs per second, while the other 5% are in search mode. This results in an average requirement of 27 pulse pairs per second for lock-on. The output of a modern ground station is a constant 2,700 pulse pairs per second. When a ground station is receiving 2,700 pulse pairs per second, which equates to 100 aircraft at 27 pulse pairs per second, it becomes saturated, and then it reduces its gain. The effect of this is to exclude the transmissions from aircraft whose interrogation pulses are weaker. Here, we see that aircraft A to G are receiving ranges from the ground station, with B just entering the coverage. When the transponder becomes saturated, the transmission intensity is reduced, so that aircraft A, B, E, F and G will be excluded and unlock. This gives preference to the aircraft with the strongest signal, in this case C and D. To facilitate and speed up frequency selection and to reduce the pilot's workload, VORs may be frequency paired with a DME or TACAN installation. So, when the VOR frequency is selected, the DME is also selected. Ideally, both sets of equipment should be located in the same place, but this is not always possible. The term associated is used to denote that the equipment is either co-located or close enough to make no significant difference. For a terminal VOR, this is defined as a maximum of 30 meters. For an en route VOR, the maximum is 600 meters. If the VOR and DME are not associated, for example, a terminal DME which is more than 100 feet from the VOR, but they are using the same location, then the first two letters of the equipment are the same, but the third letter of the DME is the letter Z. If the VOR and DME equipment are at entirely different locations, which is deemed to be more than 6 nautical miles apart, then the equipment is not paired, and the idents are different. Based on a 95% probability, the system accuracy for DME used for navigation should give a total system error not exceeding plus or minus 0.25 of a nautical mile, or plus or minus 1.25% of range, whichever is larger. This is called DMEN, where the N stands for narrow spectrum. Precision systems, DMEP, should have errors not exceeding plus or minus 0.2 of a nautical mile. You will recall that DME does not measure ground distance below the aircraft to the station, but the slant range of the aircraft to the station. This does not cause a problem when the aircraft range is more than 3 times height, but when the aircraft is close to the station, the plan range will become increasingly inaccurate. Similarly, if the DME has a ground speed computation facility, when the aircraft is above the station, the computed ground speed will be 0 knots. Also, if an aircraft flies a range arc from a DME, the distance does not change. So, a ground speed is only valid when an aircraft is flying directly to or from the station. When DME is paired with ILS, the transponder is adjusted to give range to the threshold. This is achieved by reducing the time delay at the transponder, so that the time taken for the interrogation pulse to travel from the threshold to the station and the response back to the threshold and the delay total 50 microseconds. This would be the time taken if the equipment were at the threshold. However, the range is not valid if measured from any other direction. In considering maximum range, DME is limited by line of sight. The higher the aircraft and the DME station, the longer the range. In general, DME readouts do not exceed 275 nautical miles, this being the maximum range at which an aircraft at 50,000 feet would receive a ground beacon at sea level. In order to overcome range errors, which may be caused by mutual interference between 2 or more facilities sharing the same frequencies, a designated operational coverage, or DOC, is published for each DME. This protects the DME from co-channel interference under normal propagation conditions. The DOC is specified as a range and height, for example, 20 nautical miles at 24,000 feet. The use of a DME beyond its DOC limitations may result in range errors. Let's summarize this lesson. The principle of DME is that it measures slant range by secondary radar, that is, transponder technique. The aircraft transmits on an interrogation frequency, and the response frequency differs by 63 MHz. The frequencies used are 962 to 1213 MHz in the UHF band at 1 MHz spacing. This provides 252 channels. The transmitter searches at 150 pulse pairs per second for 100 seconds, or until lock-on. If, after 100 seconds, lock-on is not achieved, the search reduces to 60 pulse pairs per second until lock is achieved, or a new channel is selected. At lock-on, the rate reduces to 25 pulse pairs per second. The ground station transmits 2,700 pulse pairs per second. The aircraft DME recognizes replies to its own interrogation by jittering the PRF of the interrogation pulse pairs. The system saturates if more than about 100 aircraft interrogate simultaneously. The weakest signals are discarded as the transponder gain is reduced. There is a 50 microsecond delay at the transponder. Remember to subtract if you are required to do any slant range calculations. If you have to calculate plan range from slant range, use Pythagoras' theorem. Associated VORs and DMEs must be within 30 meters for a terminal VOR and within 600 meters for an en route VOR. Co-located VOR DMEs have the last letter of the DME identifier changed to Z. Any ground speed calculated is most accurate when flying directly towards or away from the beacon and at longer range. DMEs associated with ILS installations are zero-ranged to the runway threshold by adjusting the time delay at the transponder. The accuracy for a DME N is plus or minus 0.25 of a nautical mile, or 1.25% of range, whichever is the greater. The accuracy for a DME P is plus or minus 0.20 of a nautical mile. This concludes the lesson on DME.